Section 6.5 is about solving linear differential equation. We'll learn this sequence, and we know that this is a geometric sequence, and we know that uk is equal to a to the k u0, and we know that if a absolute value is less than 1, and then limit k infinity uk will be 0. So we know that, and we know if a is 1 and uk, I mean the limiting value is equal to u0, and if a is equal to -1, and then there's an oscillation, because we will get this will be u0 minus u0 and u0 and minus u0. So we have oscillation for this case. And then we learn this is vector, and a times uk, and this problem is related to eigenvalue. So we solve this equation using eigenvalue, and then what we need to do is diagonalization of a first, and then so we write a to x times lambda x inverse, and we also decompose the initial condition vector, because we have u0, and then but we're gonna decompose the vector into this form, x times some c vector, and you need to find the c vector because we have initial condition u0, but we need to find the c vector, which is the coefficient when we represent the initial condition vector as a linear combination of eigenvectors, because x, right now the x matrix is an eigenvector matrix, and in that case uk will be a to the k u0, and that'll be x lambda to the k x inverse, and the u0 is here, so we plug in, and then we have xc. So I think I have to write, and so uk will be x times lambda to the k and the c vector. And so we and then we know that if eigenvalue, because the initial vector has a the eigenvalue -1 component, and the vector will oscillate, and other vector will fade out if the absolute value of eigenvalue is less than 1, and then it'll gonna fade out. And so we learn two things, which is sequence. I mean, when we deal with discrete time system, I think they are a discrete time system. So this discrete time system. But the first one is a single variable, and this red one, and this is about we have a state vector. So we're dealing with multi-variable, and we're dealing with evolution of it as dynamics, but it's discrete time. So we learn that first. Now we want to think about the continuous time system. So this is about continuous time system. So this is just one variable. We have u, and we solved this differential equation before. I hope so. You did it before. And in this case, u of t will be c times e to the at. And well, if you plug in, you can verify that easily. And so given u0, this is initial condition, and so u of t will be u0 and e to the at. And as we know, if a is 0, we're gonna have u of t will be u0 and stay forever. And if a is less than 0, it'll fade out. So we know limit t goes to infinity, and u of t will be 0. And yeah, so and then if a is big, and also what else? If a is a complex, it'll oscillate. And for example, if a is just a complex number, and then it'll oscillate. There will be oscillation. So we know these things already, and what we want to do is we want to solve this equation. U of t now is a vector, and yeah, this is a differential equation, and I think a differential equation of this thing is a simplest one, because we have only one variable u. But right now u is a vector with n variable. So right now is u of t. I mean the a vector is n by n, and the initial condition u vector 0 is given. The initial vector or initial condition is given. And well, you expect u of t will be e to the at and u0 vector. So we expect that. So yeah, we'll see how can we calculate this term e to the at, because a is right now a matrix. So but we're gonna use the Taylor series, because in Taylor series we have e to the t, which is 1 plus t plus t squared plus t to the cube and 3 factorial, something like that. And then we plug in at. And so in that case we put a here, and we put so it'll change to I, identity matrix, and it's going to be at, and then it's going to be at squared, something like that. And so in that sense, we can calculate e to the at when A is a matrix. So we're going to verify that, and then yeah, we're going to change the we're gonna solve for that e to the at, and then it's going to be simplified using eigenvalue and eigenvector, and that's the topic of in this section. So we'll talk about solution of du dt is equal to a times u of t, and we'll see example. And the A matrix now is given as 0, 1, 1, 0, and the initial vector is 4, 2. And if we plug in like this one, u is just e to the lambda t, it's just a guessing, times x vector. We plug in to the differential equation here, and what we get is du dt is yeah, as a differentiation is lambda e to the lambda t x, and well, so we plug in this to this differential equation. What we get is lambda e to the lambda t x vector is a e to the lambda t x vector. So we cancel out this vector and this vector. So what we have is lambda x is equal to ax. So we can see that thus e to the lambda t times x vector is a solution of differential equation du dt equal to a times u of t. If lambda is an eigenvalue, and I have no space, and x is the corresponding eigenvector. So well, this is the conclusion. So this will be solution of the differential equation if lambda is an eigenvalue and the x vector is an eigenvector. So we back to the eigenvalue of A matrix. A matrix is 0, 1, 1, 0. This is a 2 by 2 permutation matrix, and if we calculate the eigenvalue, which is 1 and minus 1, and the 2 is minus 1, and the corresponding eigenvector is 1, 1, and eigenvector is 1 minus 1. So u1 of t is e to the lambda 1 t x1 will be e to the t 1 1 ut u2 of t, which is e to the lambda 2 t x2 vector, which is minus t e to the minus t 1 minus 1. And we see that so lambda 2 is minus 1, which is less than 0. So we expect this term, this term will fade out, will decay. Will decay because lambda 2 is negative. So the complete solution will be linear combination of this and c times e to the t. C is just an arbitrary number, real number, and d times e to the minus t 1 minus 1. But we need to find c and d. We just solve this equation. This is for 2 initial condition, so c times 1, 1 plus d times 1 minus 1. Solving this equation, we can get c and d. So we summarize the procedure for solving this differential equation, and we assume that the initial condition is given, and A matrix is n by n scale matrix. And first we need to do write initial condition vector as a linear combination of eigenvectors x1 and xn. They are eigenvectors. Eigenvectors of A. This process is always necessary. And then we can have the coefficient C1, C2, and Cn. They are found. And second, we multiply the eigenvector by its growth factor. We call it growth factor, which is e to the lambda it. And the number 3 is u vector. The solution will be, so we get a solution, e to the lambda 1t x1 plus cn times e to the lambda nt and xn, which is eigenvector. And if A is not diagonalizable, growth factor and t e to the lambda t and t square e to the lambda t cube e to the lambda t should be used. And I think it's, this case, A is not diagonalizable. I think we won't cover this. I think we don't need to cover this case. And, you learn this thing when you talk about critically damping when we have a repeated roots, repeated eigenvalue. But I think we're not going to concentrate on this case. I mean, when A is not diagonalizable, because this course is just the introduction to linear algebra. Example 2 is about differential equation, and the initial condition is 974, and the eigenvalue of A is 1, and eigenvector is 1, 0, 0, and the second eigenvector is 2, and the corresponding eigenvector is 1, 1, 0. and the third eigenvalue is 3, and the corresponding eigenvector is 1, 1, 1. And after that, we represent the initial condition vector as a linear combination of eigenvectors. And the basis of the solution space will be u1 of t, which is e to the t x1, and u2 of t, and e to the 2t x2, and u3 t will be e to the 3t x3. And so the solution will be u of t is equal to 2 times e to the t x1 plus 3 times e to the 2t x2 plus 4 e to the 3t x3. Yeah, so in this way we can solve this linear differential equation. First we get eigenvalue and eigenvector, and then we represent the initial condition vector into a linear combination of eigenvectors, and yeah, and it's very easy, and then we can find the basis for the solution space using eigenvalue and eigenvector here. And then we write as a linear combination of a basis, and the coefficient comes from the linear combination representation of initial condition vector, and that way we can find the solution of this linear differential equation. We'll talk about second order differential equation, and we want to solve this a differential equation, and we write in this way: dy dt is equal to y prime. Yeah, this is just a definition, and dy prime dt, which is double prime, is equal to ky minus by prime. So together we can write this as d dt y prime is equal to 0, 1 minus k minus b y prime. And we can write as this a u vector. And so we have du dt is equal to aut. But we know how to solve it. First we calculate eigenvalue of this matrix, minus k minus b minus lambda. And so determinant of a minus lambda I lambda square plus b lambda plus k is equal to 0. So in this way, so we can have eigenvalue, and then we can get eigenvector, and if we have initial condition, and then we can represent the initial condition vector into a linear combination of eigenvectors, and in that way we can solve this second order equations. We consider undamped oscillation, so there is no damping. So we have this differential equation, and we guess the solution is in this type, in this function, and we plug in, what we get is lambda squared plus 1 is equal to 0. So lambda is plus minus I, and so we can find that the basis of the solution space will be e to the it and e to the minus it. And so we know that in this case, because the solution basis could be cosine and sine. So we know that the solution will be this c2 sine t. Yeah, because cosine is just cosine t is just 2 e to the it plus e to the minus it. So we know that. So, and this is the solution for this second order linear differential equation. But we can solve this equation using matrix. So u of t, we just write it as y prime, and then du dt will be d dt, which is u is equal to y prime, and it'll be 0 1 minus 1 0 and y prime. In this example, we know that this is a u of t. But we know that eigen values of this matrix 0 1 minus 1 0, we know that this is plus minus I. That's why we have plus minus I here, and so we introduce the. So this is the way of using a matrix to solve differential equation. Maybe you learned the first method in engineering mathematics course, but we can use linear algebra. Now we will talk about stability of 2x2 matrices. And when we have this differential equation, and u of t is a state vector, and also there is no input to this system. No input in this system. So the response it's only by the initial condition. Only the initial condition exists. So the question is, if there is no input to this system, we have a state vector, and the question is whether u of t goes to 0 vector as time goes to infinity. If this is correct, then we say this system is stable. And but we know that u of t will be c1 e to the lambda 1t times x1 vector, which is eigenvector, and c2 e to the lambda 2t x2. So for stability, I mean real part lambda 1 and real part of lambda 2 should be negative for stability. And for example, if 2x2 matrix case, A will be A, B, C, D, and this is a real matrix, And as we know, lambda 1 plus lambda 2 is trace, so a plus d should be negative, and lambda 1, lambda 2, which is AD minus BC, should be positive, because, lambda 1 and the real part of lambda 1 and lambda 2 should be negative for stability. So if we consider this real matrix, and the trace is negative, and a determinant is positive, then we can say this system, this system is stable. We'll talk about the exponential of a matrix. We know that a dy dt is equal to a times y of t. In that case, y of t will be e to the at y0. So when we talk about this differential equation, what we want is solution could be written as e to the at and u0. Yeah, that is what we want. So we define e to the at. So this is definition. So we define in this way: I plus at plus 1/2 at square plus 1/3 factorial at cube plus, and so on. This is just a definition using Taylor series, but A is right now matrix, and then we can say dt we differentiate, and we can see that a plus a square t plus 1/2 factorial a cube t square plus, and so on. And it's just a times e to the at. So in this case, we know that I plus at plus 1/2 at square plus x vector is, when we multiply, and we know that this is 1 plus lambda t plus 1/2 lambda t square plus, and so on, x vector. The x vector here is eigenvector. This is eigenvector, and x vector is eigenvector. And the lambda here is eigenvalue. And the reason is that since ai x is equal to lambda to the I x for eigenvalue and eigen a vector, this is true. Now we know that from this equation, we know that I think I have to erase that part, maybe this part. And from this, we know that, what is that? This is e to the at times x vector is just e to the lambda t times x vector. So we can write in this way: if x vector is eigenvector, if x is an eigenvector. So now we can say that the matrix here, the matrix is e to the at. We have matrix here, e to the at. What is e to the at's eigenvalue of e to the at? So this is matrix e to the at, and we want to find the eigenvalue of it. Eigenvalue is e to the lambda t. So we know that e to the at, eigenvalue of e to the at is equal to e to the lambda t. And what is eigenvector? Eigenvector is just x. Is the eigenvector corresponding to lambda, and that is the eigenvector. So this equation is used later. So we have e to the at matrix. We want to find the eigenvalue. What is the eigenvalue? That is e to the lambda t is the eigenvalue for the matrix e to the at. So we could write u of t is equal to e to the at. U0 is the solution. It is the solution because du dt is d dt e to the at u0, and because u of 0, this is just a constant vector, so it's just a constant, and we know that this is just a times e to the at. We derived in a previous slide, and it'll be u0 because u0 vector, initial vector, is just a constant, but we know that this is u of t. So we can write this is just a u of t. So that's why this is a solution for the differential equation. And well, the question is how to find, we want to know how to find e to the at, and we're going to drive it next page. So e to the at is by definition I plus at plus 1 over 2 factorial a square t square plus 1 of 3 factorial a to the cube t cube plus and so on. And this is I plus, if we have eigen decomposition, we have x lambda x inverse t plus 1 over 2 factorial x lambda x inverse and x lambda x inverse t square and so on. And we have x times I plus lambda t plus 1 over 2 factorial lambda t square plus and so on x inverse. And x is the eigenvector matrix for matrix A. And this is x times e to the lambda t by definition, and x inverse. And this is x, but e to the lambda t, and this is just e to the lambda 1t and e to the lambda 2t and so on. e to the lambda nt, and they are all 0, and x inverse. We already know that the eigenvalue of e to the at is just e to the lambda t. So that's why we have all of this, because we derived that relation before in previous slide, and at and x vector is just e to the lambda t x. When x vector is an eigenvector and a lambda is eigenvalue of a, and we know that this is true, so we use that, and so we can go directly here. So because this the eigenvector of this matrix is just this, so we can go directly. But anyway, we derived other way. So so now we did eigen decomposition for the matrix e to the at. So this one, I mean, this is the what is this? This is the eigen decomposition composition of e to the at. So this is an example of differential equation, and the initial condition is just a 2, 1 vector, and for this matrix, and lambda 1 is equal to 1, and eigenvector is 1, 0, and the lambda 2 is 2. Again, vector for this is 1, 1, and so we know that solution will be e to the at times u 0, and so we know that this is 1, 0, 1, 1, which is eigenvector matrix, and this will be e to the t 0, 0, e to the 2t, because we know that the eigen value of this matrix will be e to the lambda t. So that's why we have this and this. And then we write 1, 1, 0, 1 inverse here. This is the end of section 6.5.